Last time I spent solving a system of equations dealing with the chilling of this hard-boiled egg being put in an ice bath. We called T1 the temperature of the yolk and T2 the temperature of the white. What I'm going to do is revisit that same system of equations, but basically today, the topic for today is to learn to solve that system of equations by a completely different method. It's the method that's normally used in practice. Elimination is used mostly by people who've forgotten how to do it any other way. Now, in order to make it more, a little more general, I'm not going to use the dependent variables T1 and T2 because they suggest temperature a little too closely. Let's change them to neutral variables. I'll use x equals T1, and for T2 I'll just use y. So I'm not going to rederive anything. I'm not going to resolve anything. I'm not going to repeat anything of what I did last time, except to write down, remind you of what the system was in terms of these variables, the system that we derived using the particular conductivity constants 2 and 3 respectively. The system was this one, minus 2x plus 2y, and the y prime was 2x minus 5y. And so we solved this by elimination. We got a single second order equation which we solved with constant coefficients, which we solved in the usual way. From that I derived what the x was. From that we derived what the y was, and then I put them all together. So I'll just remind you of what the final solution was when written out in terms of arbitrary constants. It was C1 times e to the negative t plus, I forget, C2, e to the negative 6t. And y was C1 over 2, e to the negative t plus minus 2C2, e to the negative 6t. That was the solution we got. And then I went on to put in initial conditions, but we're not going to do that, explore that aspect of it today. We will in a week or so. So this was the solution, the general solution, because it had two arbitrary constants in it. What I want to do now is revisit this and do it by a different method, which makes heavy use of matrices. So that's a prerequisite for this course. So I'm assuming that you reviewed a little bit about matrices, and it's in your book. Your book puts in a nice little review section. 2 by 2 and 3 by 3 will be good enough for 1803, mostly because I don't want you to calculate all night on bigger matrices, bigger systems. So, matrix, nothing serious. Matrix multiplication, solving systems of linear equations, n by n systems. I'll remind you at the appropriate places today of what it is you need to remember. So the very first thing we're going to do is, let's see, maybe I haven't figured out the color coding for this lecture yet, but let's make the system in green, and the solution can be in purple. Invisible purple. But I have a lot of it. Okay. All right. So let's abbreviate, first of all, the system using matrices. I'm going to let xy, I'm going to make a column vector out of xy. Then you differentiate a column vector by differentiating each component. So I can write the left-hand side of the system as xy prime. How about the right-hand side? Well, I say I can write that, just write the matrix of coefficients, negative 2 to negative 5 times xy, and I say that this matrix equation says exactly the same thing as that green equation, and therefore it's legitimate to put it up in green too. Doesn't it? Let's see. The top here is x prime. What's the top here. This, after I multiply these two, I get a column vector. And what's its top entry? It's negative 2x plus 2y. There it is. And the bottom entry, the same way, is 2x minus 5y, just as it is down there. Okay. Now, what I want to do is, maybe I should translate the solution. What does the solution look like? All right, we got that too. xy equals, how am I going to write this as a matrix equation? Now, actually, this is, if I told you to use this, use matrices, use vectors, the point at which you might be most hesitant is this one right here, the very next step. Because how you should write it is extremely well concealed in this notation. But the point is, this is a column vector, and the sum of these, I'm adding together two column vectors, and what's in each one of the column vectors? Both, think of these two things as a column vector. Pull out all the scalars from them that you can. Well, you see that C1 is a common factor of both entries, and so is e to the negative t, that function. Now, if I pull both of those out of the vector, what's left of the vector? Well, you can't even see it. What's left is a 1 up here and a 1/2 there. So I'm going to write that in the following form. I'll pull out the C1, that's the common factor in both, and put that out front. Then I'll put in the guts of the vector, even though you can't see it, the column vector 1, 1/2, and then I'll put the other scalar factor, scalar function, in back. The only reason for putting one of these in front and one in back is visual, so to make it easy to read. There is no other reason. You could put the C1 here, you could put it here, you could put the e negative t in front if you want to, but people will fire you. I mean, don't do that. Write it the standard way, because that's the way that it's easiest to read. The constants out front, the functions behind, and the column vector of numbers in the middle. And so the other one will be written how? Well, here, that one's a little more transparent. C2, 1, 2, and the other thing is e to the negative 6t. So there's our solution. That's going to need a lot of purple, but I have it. Okay. And now I want to talk about how the new method of solving the equation. It's based just on the same idea that the way we solved second-order equations. Yes, question? Is what? Oh, here, sorry, this should be negative 2. Thanks very much. What I'm going to use is a trial solution. Remember when we had a second-order equation with constant coefficients? The very first thing I did, I said, okay, we're going to try a solution of the form e to the lambda, e to the RT. Why that? Well, because Euler thought of it, and it's been known for 200 or 300 years that that's the thing you should do. Well, this hasn't been known nearly as long, because matrices were only invented around, 1880 or so. And people didn't really use them to solve differential equations, systems of differential equations, until the middle of the last century, 1950, 1960. If you look at books written in 1950, they won't even talk about systems of equations, differential equations. Or they'll talk very little anyway, and they won't solve them using matrices. So this is only 50 years old. I mean, my God, in mathematics, that's very up to date. Okay, particularly elementary mathematics. Anyway, I'm going to, the method of solving is going to use as a trial solution. Now, the form of if you were left to your own devices, you might say, well, let's try x equals some constant times e to the lambda 1t, and y equals some other constant times e to the lambda 2t. Okay, we'll go in. Now, if you try that, it's a sensible thing to try, but it will turn out not to work. And that's the reason I've written out this particular solution, so we can see what solutions look like. The essential point is, here's my solution, the basic solution I'm trying to find. Here's another one. their form is a vector of constants, a column vector of constants, but the exponential factor, they both use the same exponential factor. That's the point. In other words, I should not use here in my trial solution two different lambdas. I should use the same lambda. And so the way to write the trial solution is xy equals two unknown numbers, that or whatever, times e to an single unknown exponential exponent factor. Let's call it lambda t. It's called lambda, it's called r, it's called m. I've never seen it called anything but one of those three things. But I'm using lambda. Your book uses lambda. It's a common choice. Let's stick with it. Okay, now what's the next step? Well, we plug in to the system. So substitute into the system. What are we going to get? Well, let's do it. First of all, I have to differentiate. The left-hand side asks me to differentiate this. How do I differentiate this? Column vector times a function. Well, the column vector acts as a constant, and I differentiate that. That's lambda e to the lambda t. So it's the xy prime is a1, a2 times e to the lambda t times lambda. Now, it's ugly to put the lambda afterwards because it's a number, so you should put it in front. Again, to make things easier to read. But this lambda comes from differentiating e to the lambda t and using the chain rule. So this much is the left-hand side. That's the derivative xy prime. I differentiated the x and I differentiate the y. How about the right-hand side? Well, the right-hand side is negative 2, 2, negative 5, times what? Well, times xy, which is a1, a2, e to the lambda t. Now, the same thing that happened a month or a month and a half ago happens now. The whole point of making that substitution is that the e to the lambda t, the function part of it, drops out completely. And one is left with what? An algebraic equation to be solved for lambda, a1, and a2. In other words, by means of that substitution, and it basically uses the fact that the coefficients are constant, what you've done is reduce the problem of calculus, of differential equations, of solving differential equations to solving algebraic equations. In some sense, that's the only method there is, unless you do numerical stuff. You reduce the calculus to algebra. The Laplace transform is exactly the same thing. All the work is algebra. You turn the original differential equation into an algebraic equation for y of s. You solve it, and then you use more algebra to find out what the original y of t, little y of t was. It's no different here. Okay, so let's solve this system equation. Now, the whole problem with solving this system, first of all, what is the system? Let's write it out explicitly. Well, it's really two equations, isn't it? The first one says lambda a1 is equal to negative 2a1 plus 2a2. That's the first one. The other one says lambda a2 is equal to 2a1 minus 5a2. Now, purely if you want to classify that, that's two equations in three variables, three unknowns. The a1, a2, and lambda are all unknown. And unfortunately, if you want to classify them correctly, they are nonlinear equations because they're made nonlinear by the fact that you've multiplied two of the variables. Well, if you sit down and try to hack away at solving those without a plan, you're not going to get anywhere. It's going to be a mess. Also, two equations and three unknowns is indeterminate. You can solve three equations and three unknowns and get definite answer, but two equations and three unknowns usually have an infinity of solutions. Well, at this point is the only idea that's required. Well, this was a little idea, but I assume one would think of that. And the next one is, the idea that's required here is, I think, not so unnatural. It is not to view these A1, A2, and lambda as equal. You know, not all variables are created equal. Some are more equal than others. A1 and A2 are definitely equal to each other. And let's relegate lambda to the background. In other words, I'm going to think of lambda as just a parameter. I'm going to demote it from the status of variable to a parameter. If I demoted it further, it would just be an unknown constant. That's as bad as you can be. So I'm going to focus my attention on the A1, A2, and sort of, you know, view the lambda as a nuisance. Now, as soon as I do that, I see that these equations are linear if I just look at them as equations in A1 and A2. And moreover, they're not just linear, they are homogeneous. Because if I think of lambda just as a parameter, I should write the equations, I should rewrite them this way. Minus 2, I'm going to subtract this and put the left, I'm going to move the left-hand side to the right side, and it's going to look like minus 2 minus lambda times A1 plus 2A2 is equal to 0. And the same way for the other one, it's going to be 2A1 plus, what's the coefficient? Minus 5 minus lambda, A2. That's a pair of simultaneous linear equations for determining A1 and A2, and the coefficients involve a parameter, lambda. Now, what's the point of doing that? Well, now the point is, whatever you learned about linear equations, you should have learned the most fundamental theorem of linear equations. The main theorem is that you have a square system of homogeneous equations. This is a 2-by-2 system, so it's square. It always has a trivial solution, of course, A1, A2 equals 0. Now, we don't want that trivial solution because if A1 and A2 are 0, then so are X and Y 0. Now, that's a solution, unfortunately, it's of no interest. If the solution where X and Y are 0 corresponds to the fact that this is an ice bath, the yolk is at 0, the white is at 0, and it stays that way for all time until the ice melts. So that's the solution we don't want. We don't want the trivial solution. Well, when does it have a non-trivial solution? Non-trivial. That means non-zero, in other words. Solution, if and only if, this determinant is 0. In other words, what we find is there's a condition on lambda. By using that theorem on linear equations, what we end up with is a condition that lambda must satisfy, an equation in lambda, in order that we be able to find the non-zero values for A1 and A2. So let's write it out. I'll recopy it over here. It's negative, what was it? Negative 2 minus lambda. 2 here. Here it was 2 and minus 5 minus lambda. All right, let's, this is an equation. You know, you have to expand the determinant. In other words, we're trying to find out for what values of lambda is this determinant 0. Those will be the good values which lead to non-trivial solutions for the A's. All right, so this is the equation 2. So this is lambda plus 2. See, if I multiply, this is minus that and minus that. The product of the two minus 1s is plus 1. So it's lambda plus 2 times lambda plus 5. That's the product of the two diagonal elements, minus the product of the two anti-diagonal elements, that's 4, is equal to 0. And if I write that out, so what is that? That's the equation lambda squared plus 7 lambda, right? 5 lambda plus 2 lambda. And then the constant term is 10 minus 4, which is 6. How many of you have long memories long enough memories, 2-day memories that remember that equation. When we did the elimination, when I did the method of elimination, it led to exactly the same equation, except it had r's in it instead of lambda. And this equation, therefore, is given the same name and another color. Let's make it salmon. So this is our, and it's given the same name of, this is called the characteristic equation. For this method. All right, I'm going to use now the work from last time. You factor this. From the factorization, we get its roots easily enough. The roots are lambda equals -1 and lambda equals -6 by factoring the equation. Now what am I supposed to do? You have to keep the different parts of the method together. Okay, now I've found the only values of lambda for which I will be able to find non-zero values for the A1 and A2. So for each of those values of lambda, I now have to find the corresponding A1 and A2. So let's do them one at a time. So let's take first lambda equals -1. My problem is now to find A1 and A2. Where am I going to find them from? Well, from that system of equations over there. I'll recopy it over here. What is the system? Okay, if lambda is -1, -2, the hardest part of this is dealing with the multiple minus signs, but you've had experience with that at determinants, so you know all about that. Okay, so in other words, there's the system of equations over there. The question is, let's recopy them here. So -2 minus -1 makes well, that makes -1. Okay, what's the other coefficient? It is just plain old 2. Good. So there's my first equation. And when I substitute lambda equals -1 for the second equation, what do you get? 2A1 plus -5 minus -1 makes -4. There's my system for finding that will find me A1 and A2. Now, what's the first thing you notice about it? Well, you immediately notice that this system is fake because this second equation is twice the first one. So something's wrong. No, something's right. If that did not happen, if the second equation were not a constant multiple of the first one, then the only solution of the system would be A1 equals 0, A2 equals 0. Because the determinant of the coefficients would not be 0. The whole function of this exercise was to find the value of lambda, -1, for which the system would be redundant and therefore would have a non-trivial solution. You get that? So in other words, calculate the system out, just as I've done here. You have an automatic check on the method. If one equation is not a constant multiple of the other, you made a mistake. You don't have the right value of lambda, or you substituted into the system wrong, that's frankly a more common error. You substituted into the system wrong. Go back, recheck first the substitution, and if you're convinced that's right, then recheck where you got lambda from. Okay, but here everything's going fine, so we can now find out what the value of A1 and A2 are. Now, this is usually, since you don't have to go through a big song and dance for this, since most of the time you'll have 2x2 equations and now and then 3x3. For 2x2, all you do is, since we really have the same equation twice, I can assign, to get a solution, I can assign one of the variables any value and then simply solve for the other. the natural thing to do is to make A2 equal 1. Then I won't need fractions. Then A1 will be 2. So a solution is... I'm only trying to find one solution. Any constant multiple of this would also be a solution, as long as it wasn't 0, 0, which is the trivial one. And therefore, so this is the solution to this system of algebraic equations, and the solution to the whole system of differential equations, then, is this is only the A1, A2 part. I have to add to it, as a factor, the e to the, well, lambda is negative 1, and therefore e to the minus t. There's our purple thing. See how I got it? Starting with the trial solution, I first found out through this procedure what the lambdas have to be. Then I took the lambda, found what the corresponding A1 and A2 that went with it, and then made up my solution out of that. Now, quickly, I'll do the same thing for lambda equals negative 6. Each one of these must be treated separately. They're separate problems. You're looking for separate solutions. Okay, for lambda equals negative 6, what do? How do my equations look now? Well, the first one is minus 2 minus negative 6 makes plus 4. So it's 4a1 plus 2a2 equals 0. And then I hold my breath while I calculate the second one to see if it comes out to be a constant multiple. So I get 2a1 plus negative 5 minus negative 6. That makes plus 1. Negative 5 minus negative 6 is plus 1. And indeed, one is a multiple, a constant multiple of the other. I really only have one equation there, and therefore the A1, A2, for the A1, I'll just write down immediately now what the solution is to the system. Is, well, the A1, A2 will be what? Now it's more natural to make A1 equal 1 and then solve to get an integer for A2. If A1 is 1, then A2 is negative 2. And I should multiply that by e to the negative 6t, because this is negative 6 is the corresponding value. So there's my other one. And now there's a superposition principle, which if I get a chance, I'll prove for you at the end of the hour. If not, you'll have to do it for yourself for homework. So by the superposition, once you have, since this is a linear system of equations, once you have two separate solutions, neither a multiple or constant multiple of the other, you can multiply each one of these by a constant and it will still be a solution. You can add them together and that will still be a solution, and that gives the general solution. So the general solution is the sum of these two. An arbitrary constant, I'm going to change the name since I don't want it to confuse it with the C1 I used before, times the first solution, which is 2, e to the negative t, plus C2, another arbitrary constant, times 1, negative 2, e to the minus 6t. Now you notice that's exactly the same solution I got before. The only difference is that I've renamed the arbitrary constants. The relation between them is that what I'm calling 1/2, what I C1 over 2 was, I'm now calling C1 tilde, and C2, I'm calling C2 tilde. It doesn't, if you have an arbitrary constant, it doesn't matter whether you divide it by 2, it's still just as arbitrary a constant. It covers all values, in other words. Well, I think you'll agree that's a different procedure. It's a different procedure. Yet it has only one coincidence, namely, it's like elimination goes this way and comes to the answer, and this method goes a completely different route and comes to the answer, except it's not quite like that. They walk like this, and then they come within viewing distance of each other to check that both are using the same characteristic equation, and then they go their separate ways and end up with the same answer. So there's something special about the values of, you cannot get away from those two values of lambda. Somehow they're really intrinsically connected. They occur as the exponential coefficients, and they're intrinsically connected with the problem of the egg that we started with. Okay, now what I'd like to do is very quickly sketch how this method looks when I remove all the numbers from it. In some sense, it becomes a little clearer what's going on, and that will give me a chance to introduce the terminology that you need when you talk about it. So, let's see. Okay, well, you got notes. Let me try to write it down in general. I'll first write it out by 2 by 2. So I'm just going to sketch. So the system looks like xy equals, I'll put it still up in colors. Except now, instead of using 2s and 5s, I'll use A, B, C, D. The trial solution will look how? The trial is going to be A1, A2. That I don't have to change the name of. I'm going to substitute in, and what's the result of substitution is going to be lambda A1, A2. I'm going to skip a step and pretend that the e to the lambda t's have already been canceled out, is equal to ABCD times A1, A2. What does that correspond to? That corresponds to the system as I wrote it here. And then we wrote it out in terms of two equations. And what was the resulting thing that we ended up with? Well, you write it out, you move the lambda to the other side, and then the homogeneous system will look in general how? Well, we can write it out. It's going to look like A minus lambda, B, C, D minus lambda. That's just how it looks there. And the general calculation is the same. Times A1, A2 is equal to 0. Now that is solvable. This is solvable non-trivially. In other words, has a non-trivial solution if and only if this determinant is 0. The determinant of coefficients is 0. Okay, let's now write that out, calculate out once and for all what that determinant is. Okay, it's going to be, I'll write it out here. So it's A minus lambda times D minus lambda, that's the product of the diagonal elements, minus the anti-diagonal, minus BC is equal to 0. And let's calculate that out. It's lambda squared minus A lambda minus D lambda plus AD is the constant term from here, negative BC from there. So plus AD minus BC. Where have I seen that before? So this equation is the general sorry. Carried away here. That equation is the general form using letters of what we calculated using the specific numbers before. So again, I'll code it the same way with, what's that color is that? Salmon. most of your calculations will be for 2 by 2 systems. I advise you in the strongest possible terms to remember this equation. You can write down this equation immediately from the matrix. You don't have to go through all this stuff. For God's sakes, don't say, let the trial solution be blah, 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 blah. You don't want to do that. I don't want you to repeat the derivation of this every time you go through a particular problem. It's just like in solving second-order equations. You immediately write down, you have a second-order equation, you immediately write down its characteristic equation, then you factor it, you find its roots, and you construct the solution. It takes a minute. The same thing, this takes a minute too. Now, what is this? Remember, what's the constant term? AD minus BC, what's that? Matrix is A, B, C, D. AD minus BC is its determinant. This is the determinant of that matrix A. I didn't give the matrix a name, did I? Okay, I will now give the matrix a name A. What's this? Well, you're not supposed to know that until now. I'll tell you. This is called the trace of A. Put that down in your little books. The abbreviation is trace A, and the word is trace. The trace of a square matrix is the sum of the elements down its main diagonal. If it were a 3 by 3, there would be 3 terms in that. A, I don't know what your A, whatever you're up to. But here it's A plus D, the sum of the diagonal elements. So you can immediately write down this characteristic equation. Let's give it once more its name. So this is the characteristic equation. Of what? Of the matrix now. Not of the system. Of the matrix. You have a 2 by 2 matrix. You can immediately write down its characteristic equation. Watch out for this sign. Minus. That's a very common error to leave out the minus sign. You must put in the minus sign because that's the way the formula comes out. Its roots. It's a quadratic equation. It will have roots. Lambda 1, lambda 2, which for the moment, let's assume are real and distinct. Okay. For the enrichment of your vocabulary, those are called the eigenvalues. There's something which belongs to the matrix A. They're 2 secret numbers that you can calculate from the coefficients A, B, and C, and D, but they're not in the coefficients. You can't look at a matrix and see what its eigenvalues are. You have to calculate something. But they are the most important numbers in the matrix. They're hidden, but they are the things that control how this system behaves. Those are called the eigenvalues. Now, there are various purists, there are a fair number of them in the world who do not like this word because it begins German and ends English. Eigenvalues were first introduced by a German mathematician. Matrices, around the time matrices came into being in 1880 or so. A little while after, eigenvalues came into being too, and since all this happened in Germany, they were named eigenvalues in German, which begins eigen and ends the value, in other words. But people who don't like that call them the characteristic values. It takes, unfortunately, it's 2 words, and it takes a lot more space to write out. An older generation even calls them something different, which you are not so likely to see nowadays, but you will in slightly older books. You can also call them the proper values. Proper is a standard characteristic is not a translation of eigen, but proper is. But it means it in a funny sense, which has almost disappeared nowadays. It means proper in the sense of belonging to. The only example I could think of it is the word property. Property is something that belongs to you. That's the use of the word proper. That's what you do. It's something that belongs to the matrix. The matrix has its proper values. It does not mean proper as in the sense of fitting and proper, or it's I hope you'll behave properly, when we go to Aunt Agatha's or something like that. But as I say, by far the most popular thing, slowly the word eigenvalues is pretty much taking over the literature. Just because it's one word, that's a tremendous advantage. Okay, now, what now is still to be done? Well, there are those vectors to be found, and then you have to then solve. So the very last step would be to solve the system to find the vectors A1 and A2. So for each lambda I, find the associated vector. The vector, we'll call it alpha I. That's the A1 and A2. Of course, it's going to be indexed by, you've got to put another subscript on it because there are two of them, and A1 and A2 is stretched a little too far. By solving the system, and the system will be the system which I'll write this way, A minus lambda, B, C, D minus lambda. It's just that system that was over there, but I'll recopy it. XY, A1, A2 equals 0, 0. And these are called the eigenvectors. Each of these is called the eigenvector associated with or belonging to, again, in that sense of property, eigenvector associated with, let's say, belonging to. I see that a little more frequently, belonging to lambda I. So we got the eigenvalues, the eigenvectors, and of course the people who call them characteristic values also call them these guys characteristic vectors. I don't think I've ever seen proper vectors, but that's because I'm not old enough. I think that's what they used to be called a long time ago, but not anymore. And then finally, then the general solution will be, by the superposition principle, xy equals the arbitrary constant times the first eigenvector times the eigenvalue times the e to the corresponding eigenvalue, and then the same thing for the second one. A1, A2, but now the second index will be 2 to indicate that it goes with the eigenvalue lambda 2, e to the lambda 2t. Okay, I've done that twice. And now in the remaining 5 minutes, I will do it a third time. Because it's possible to write this, it's still a more condensed form. And the advantage of the more condensed form is, A, it takes only that much space to write, and B, it applies to systems, not just to 2-by-2 systems, but to n-by-n systems. The method is exactly the same. So let's write it out. Let's write it out as it would apply to n-by-n systems. Okay, what's this? The vector I start with is x, y, and so on, but I'll simply abbreviate this, as is done in 1802, by x with an arrow over it. The matrix A, I'll abbreviate with A, as I did before, with capital A. And then the system looks like x prime is equal to x prime is what? AX. That's all there is to it. So there's our green system. Now notice in this form, I don't even tell you whether this is a 2-by-2 matrix or an n-by-n. And in this condensed form, it will look the same no matter how many equations you have. Your book deals from the beginning with n-by-n systems. That's one of its, in my view, is one of its weaknesses. Because I don't think most students start with 2-by-2. Fortunately, the book double talks. The theory is n-by-n, but all the examples are 2-by-2. So just read the examples. read the notes instead, which just do 2 by 2 to start out with. Okay, the trial solution is x equals what? An unknown vector alpha times e to the lambda t. Alpha is what we called A1 and A2 before. Plug this into there and cancel the e to the lambda t's. What do you get? Well, this is lambda alpha, so it's lambda alpha, well, I'll put it in for the moment, e to the lambda t equals A alpha e to the lambda t. Cancels, these two cancel, and we get the system to be solved is A alpha equals lambda alpha. And now the question is, how do you solve that system? Well, you can tell if a book is written by a scoundrel or not by how they go. A book which is, in my opinion, completely scoundrelly simply says you subtract one from the other, and without further ado writes A alpha A minus lambda. They tuck a little I in there and write alpha equals 0. Why is the I put in there? Well, this is what you'd like to write. What's wrong with this equation? This is not a valid matrix equation because that's a square n by n matrix, a square 2 by 2 matrix if you like. This is a scalar. You cannot subtract the scalar from a matrix. It's not an operation. To subtract matrices, they have to be the same size, the same shape. So what's done is you make this a 2 by 2 matrix. This is the 2 by 2 matrix with lambdas down the main diagonal and I elsewhere. And the justification is that lambda alpha is the same thing as lambda I times alpha because I is an identity matrix. Now, in fact, jumping from here to here is not something that would occur to anybody. The way it should occur to you to do this is you do this, you write that, you realize it doesn't work, and then you say to yourself, I don't understand what these matrices are all about. I think I'd better write it all out. And then you would write it all out, and you'd write it, that equation on the left-hand board there. Oh, now I see what it should look like. I should subtract lambda from the main diagonal. That's the way it will come out. And then you say, hey, the way to say lambda from the main diagonal is put in an identity matrix. That'll do it for me. So in other words, there's a little detour that goes from here to here. And one of the ways I judge books is by how well they explain the passage from this to that. If they don't explain it at all, but just write it down. They've never talked to students. They've just written books. Okay, so where do we get finally here? So the characteristic equation from that's our, I forget what color that's in, salmon. The characteristic equation then is going to be the thing which says that the determinant of that, the determinant is 0. That's the circumstances under which it's solvable. So in general, this is the way the characteristic equation looks. And its roots, once again, are the eigenvalues. And from them, you calculate the corresponding eigenvectors. Okay, go home and practice. In recitation, you'll practice on both 2 by 2 and 3 by 3 cases, and we'll talk more next time.